Hey guys, today we're going to be going over series RLC and more specifically the step response. So let's get straight into it. So previously you've seen the natural response where there's no input or a wire, just a short connecting the ends or the terminals of the RLC circuit. But now we're going to see that instead of a short, we're going to have most commonly a voltage source being input. So here we are. You can see that there is the input attached. So typically, when solving these problems, we're going to have to find the voltage across the capacitor, all right? And so we're going to do that, all right? We're going to start with the KVL. We're going to call this voltage VI, okay? So we have IR starting from the resistor plus L di dt plus the voltage across the capacitor. We're just going to leave it as V sub C. And then that equals VI. Okay? So we know from our capacity equation that first off, we need to know that all the components share the same current. So I is also equal to the current through the capacitor, which is C dV dt. Okay? So now knowing this, we're going to substitute I for C dV dt. I'm going to plug in here. We have RC dVc dt plus LC d squared dVc dt squared, and then plus V sub C equals VI. If I rearrange, we're going to get d squared Vc dt squared, dividing both sides by LC. So we're going to have R over L dVc dt plus 1 over L Vc equals Vi over LC. And if we remember from Diffie Q, we know that y of t, the solution to a differential equation, is y of t, and that equals the homogeneous solution plus the particular solution. And so the homogeneous is the natural response, and the particular is the forcing function. Forcing function response. And as we saw in parallel, we find that our particular solution equals VI. And you can go ahead and test out VI, assuming VI is constant, of course. And we'll see that VI is in fact the solution for this differential equation. So knowing this, we find that our Vc of t is equal to Vi plus our natural response form. Okay? So let's go straight to an example. Let's say we have a circuit. with an input voltage of 48 volts. We have a switch. We have a resistor, an inductor, and a capacitor. This switch will connect the circuit at t equals 0. The resistor is 1,250 ohms. The inductor has 0.1 henries, and the capacitor has 0.4 microfarads. And we're going to assume 0 initial conditions. Okay, so now what does 0 initial conditions mean? Well, this means that all initial values are 0, or basically Vc of 0 equals 0, and IL of 0 equals 0. And so we need to find Vc, V sub c of t. Okay? And so let's start by analyzing our parameters, our alpha and our W naught. And as we saw in our governing equation, our alpha is R over 2L, and our W naught is 1 over square RLC. So if we plug this into our calculator, we get that alpha is 6,250 radians per second, and our W naught is 5,000 radians per second. So knowing this, we see that our alpha is greater than our W naught. So overdamped. Our system is overdamped. Knowing this, we need to find our WD, which is alpha squared minus W naught squared. If we plug this into our calculator, we get 3,750 radians per second. And if you find the roots, S1 equals negative alpha plus their damped frequency right here equals negative alpha minus the damped frequency. And we should get negative 2,500 and negative 10,000 as our roots. So, knowing that it's overdamped, we know that the solution will take the form Vi plus the natural response form, which is A e to the S1 times t plus A e to the, or not A, B e to the S2 t. And we know that Vi is equal to 48. S1 is equal to negative 25,000 or 2,500. I'm going to write 2.5K just to shorten it. Plus B, which is equal to negative 10K times T. This is VCT. Okay. So let's start with finding our initial, or we already know our initial voltage through the capacitor from our assuming 0 initial conditions. We know that's 0. So if we plug in 0, we find that 48 plus A plus B equals 0. Let me fix this 8. So now we need to find our second equation, and we're going to start by knowing that IL equals the capacitor current, which equals C dV dt. And so we know that this is 0 from our 0 initial condition, so C dVc dt equals 0. We can just cancel this out. So we're going to derive both sides of the capacitor voltage. So the constant disappears. We have negative 2.5k times A plus or minus 10k times B. And so here we have our two equations right here and right here. If we plug this into our calculator, we should find that A equals negative 64 and B equals 16. And then plugging them into our solution, we get that the capacitor voltage is equal to 48 minus 64 times e to the negative 2.5k t plus 16 e to the negative 10k t. And that's our answer.